wonderful to be able to give this talk to you. It's a talk about a result that I showed together with Asger Turnquist in 2019, and we're still working on some of the ramifications, actually. And in this result, we answered an old question of Matthias. Matthias asked, does Ramsey regularity imply that there are no mad families? And I would like to tell you why he asked this question and also why it's still interesting today and how we solved it. Okay, I can't go to the next slide. Now I can. All right, and so the one way to explain what a mad family is what we call the infinite lottery. So actually, this is how we explained it to students once. But it's very nice, and it's made the papers. So there are a couple of newspaper articles about this infinite lottery problem that we solved. Of course, you know, it's not really about an infinite lottery. It's about mad families. But I'll tell you this little story about the infinite lottery anyway. So in the infinite lottery, a draw is an infinite sequence of natural numbers in increasing order. Of course, you get a ticket, you can buy a ticket, and you know, a ticket has several entries and you somehow want to guess the draw, right? But in this particular lottery, not only the draw is infinite, also the ticket is really large. So the ticket has many entries, not just 2 or 3, it has an entry for every real number between 0 and 1. So here is the interval from 0 to 1, and with each dot here is associated an entry in your lottery ticket. And each entry is also a set of increasing natural numbers. So when do you win this lottery? You win it if one of the entries on your ticket, one of the many, many entries, has infinite intersection with the draw, with D. And to make this a little harder or a little more non-trivial, actually, you ask that the entries all have finite intersection with each other. So whenever you look at 2 entries, they should have finite intersection somehow. You know, they shouldn't be too redundant. I mean, you don't want to guess the same number twice. And also, if you don't require this, that they have finite intersection, there's an obvious ticket that will always win, namely the ticket where every entry is just all the natural numbers, the set of all natural numbers. That's a ticket that always wins, and that's, of course, cheating. You don't want a ticket that always wins. So you could ask, in this infinite lottery, is there a ticket that always wins? An ever-winning lottery ticket? And it turns out that the answer is yes. So this was not Matthias' question. The answer is yes. In mathematics, you can prove that there is a lottery ticket in this lottery that will always win, no matter what the draw is. And such a lottery ticket is also known as a mad family. But to construct it, you need the axiom of choice, of course. I mean, well, I don't know if of course is the right way of putting it, but that's what you do. You construct it using the axiom of choice. Now, to mathematicians, they will be more familiar with this thing under the name of a maximal almost disjoint family, or abbreviated a mad family. So that's a set of infinite subsets of the natural numbers. So this symbol, in case you don't know, it means this collection of infinite subsets of n. So any 2 elements of this set A should have finite intersection. That means they should be almost disjoint. And then also A should be maximal among the almost disjoint families. So whenever you try to enlarge A, it has to lose this property of being almost disjoint. Now, such an A is exactly the same thing as an ever-winning lottery ticket in the infinite lottery. In the infinite lottery, we've associated each of these sets to a point on the real number line, and now instead of that, they're just all in one bag. All of these entries are in one huge bag, very unstructured. But other than that, it's exactly the same thing. And you have to ask here, you have to ask that it's also infinite. You want A to be infinite, otherwise this is trivial as well, because if you take, you split up the natural numbers into even and odd, that's an ever-winning lottery ticket. That's boring. We don't consider these. Now, Matthias asked if there is a connection between the existence of mad families and principles of Ramsey regularity. So a principle from Ramsey theory. Ramsey theory investigates how order arises in very large sets. So the classic example is Ramsey's theorem, also where this theory got its name from. So Ramsey's theorem says that if you color the n tuples of natural numbers in two colors, then there's always an infinite set such that all the n tuples from this set will have the same color. That's Ramsey's theorem, and it's got many interesting consequences, many strengthenings, like Semiretti's theorem, for example, that's used in number theory. So this has a lot of applications. Now, set theorists wondered what happens when you replace this n here by infinity. So instead of looking at n tuples, you look at infinite subsets of n, and you color these. And then, the analog of Ramsey's theorem where you replace n by infinity doesn't hold. So we make it into a property. We say a coloring of this sort here has the Ramsey property if there exists a monochromatic set. So there is an infinite subset of n, so that the coloring is constant on all of its infinite subsets. So usually it's not phrased in terms of colorings, but in terms of sets, but it's really the same thing. So the set X here is, if you want, it's the sets that are colored with color 0, and its complement will be the sets that are colored with number 1. So you say a set has the Ramsey property if there is a large homogeneous set. That's exactly the same thing. So all of its infinite subset are contained in X, or none of its infinite subsets are contained in X. So this is what it means to have the Ramsey property. And as I said, an analog of the Ramsey theorem doesn't hold here. So not every set has the Ramsey property. In fact, again, using the axiom of choice, Erdős and Rado showed that there's a set without the Ramsey property. And simple sets, on the other hand, always have the Ramsey property. So Galvin, Prickery, Silver, and Allentuck showed a series of results. The strongest is that analytic sets have the Ramsey property. So analytic sets aren't too complicated. So you should think of the Ramsey property as something like having a measure. It's a way of being simple. So sets with the Ramsey property are regular, they're well behaved. Simple sets always have the Ramsey property, but there are irregular sets without the Ramsey property using the axiom of choice. And in fact, you may have heard of the famous Solovay model. So Solovay produced a model of all of the axioms of set theory except for the axiom of choice, so of ZF, where every set is Lebesgue measurable. And Matthias later showed that in this model also every set has the Ramsey property. So the Ramsey property really behaves a lot like measurability, or like it's a regularity property. And shortly after, or perhaps even in the same paper, actually all of this is based on Matthias' thesis. Matthias showed, that was in 1969, by the way, that there is no analytic mad family. So also among the simple sets, if you restrict your attention to sets with a nice description, there are no mad families or no ever-winning lottery tickets. And he also showed that after collapsing a Malo cardinal, you can construct a model, an inner model of that model where you've collapsed the Malo cardinal, where there are no mad families at all. So again, choice, the axiom of choice fails in that model. Every set is measurable, every set has the Ramsey property, and also there are no mad families. So Matthias wondered two things. The first thing that he wondered is it also true that there are no mad families in Solovay's model? This was answered by Asger Turnquist only in 2015. This was asked in 1969. And he also asked does every set has the Ramsey property imply that there are no mad families? So this is the question that I want to talk about, and the solution of which I want to talk about. Because as you can see in the models that I've mentioned, always when every set has the Ramsey property, also there are no mad families, it seemed. And the two things seemed a lot to have to do with each other because of their connection with Matthias forcing. So Matthias wondered, is there a connection between the Ramsey property and the existence of mad families? And the answer is yes. And this is what we showed in 2019. So we needed to assume two things. We needed to assume a uniformization principle in the background theory. So that's what I want to talk to you about next. So suppose you've got a binary relation on a set X and some subset X prime of X, then we say a function uniformizes this binary relation on X prime if it picks something in X for every element of X prime, and what it picks, f of X, always stands in relation to X. So you can find a function, it's a selector. You can find a function which selects something in the vertical above each point in the relation. It's a kind of a weak choice principle, a weak form of the axiom of choice. And what we're actually going to need is the principle called uniformization star. So you can also think of it as uniformization on a large set. It says that whenever you have a binary relation on our favorite space, n square brackets infinity, which is total. So for everything in the horizontal, there exists something in the vertical related to it. Then there's a uniformizing function which works on a very large set. And large, by large, I mean it's a set of the form square brackets B infinity. So all the subsets of an infinite set. On all of these, your uniformization function picks witness to the fact that the vertical isn't empty. So this is the uniformization star principle. And now I can state our theorem. So our theorem says, I'm going to give you the localized version of this theorem. It says, let gamma be a point class. Now, if you don't know what a point class is, it's a level of complexity, like the analytic sets. Or if you don't know what a point class is, just imagine all the sets, all the subsets of square brackets and infinity. So suppose ZF holds and dependent choice, that's a very weak form of choice. We also suppose that this uniformization principle holds for binary relations in gamma. And we assume that every set in gamma has a Ramsey property. Then there are no mad families in gamma. This is what we showed. So if you have universal Ramsey regularity also locally in a class, then in that class, there are no mad families. So I've told you a lot about the context in which Matthias asked this question, something like 50 or maybe even 60 years ago, 50. I also want to tell you why I think it's still really interesting today. So you might know that large cardinals decide many more questions than the set theory axioms ZFC alone. And I've told you that many things are undecidable. Is every set measurable? Does every set have the Ramsey property? Does there exist a mad family? Does there exist a definable mad family? Such things are usually can't be decided on the basis of ZF, or if you talk about definable sets, they can't be decided on even on the basis of set of C. And it turns out that large cardinal axioms decide many of these questions. And this happens very often through the axiom of determinacy. So in the 80s, Woodin proved that if you have infinitely many wooden cardinals with a measurable cardinal above, so that's a large cardinal axiom, then the axiom of determinacy holds in L of R. That's a very, well, I mean, think of L of R as a very large complexity class, all the sets which are definable from real parameters. And you may know that AD implies, for example, that every set of reals is measurable. Under large cardinals, every definable set is measurable. We know that. That's a fact. It follows from large cardinals. And Wooden introduced something called AD+. It's a strengthening of AD, and it tries to axiomatize the theory of AD in L of R. And AD+ decides many more things than AD by itself does. So, for example, AD+ implies that every set has the Ramsey property. And AD+ also implies that there are no mad families. And it's in both cases, it's unclear if AD itself implies it. So this is connected to the very important question whether AD+ in fact implies AD. It's not known if AD+ maybe implies AD. And Wooden has conjectured that in a much larger model than L of R, AD+ should imply AD. And so for these reasons, I think that sorting out these dependencies between the Ramsey property and mad families is still a very, very interesting question that we should think about. All right, so now I will try to tell you some ideas from the proof. I have to be a little bit sketchy on this because it's a long proof, but I'll just try to give you the spirit of it. So what do we want to show? We assume these principles of universal Ramsey regularity. Every set has the Ramsey property and this uniformization principle. And we want to show that there are no mad families. So suppose we've got a mad family, or if you like, an ever-winning lottery ticket. So first you pick an infinite sequence of elements of it, A0, A1. Of course, you want these to be pairwise different. And you fix increasing functions from n into each of these sets. And you make the ranges of these functions disjoint. Now, one of the main protagonists in this proof will be what I call the tilde operator. So to every infinite set B, we associate B tilde. B tilde comes about as follows. It's defined here. So for every two adjacent elements, n and m in B, you look at the nth function in your list and you take the image of m. So you take the mth element of AI above its intersection with the other guys for any two adjacent n and m from B. All right, so this is a map and it has very nice properties. One thing that's very nice and that's almost trivial to see is that whenever you fix some element of A, of script A, and whenever you fix a B, and then you can thin out this B so that tilde of the thinned out set is disjoint from A. And that's actually very easy to see because whenever you thin out step by step, if you've got some element that's already in your thinned out set, you can make sure that the next element comes so late that here you will be above the intersection with A. All right, so this is the first part. Now we define a relation. We say B and R are related if and only if A is in the mad family and B tilde and A have infinite intersection. So we're saying this is a mad family. So for every A, so for every B, there is an A, which will have this property. So we put that in the relation. And now we're going to pick an A by uniformization. So by uniformization star, there is a B0, and a function f from the infinite subsets of B0. Actually here, I could say into A, because f picks from the relation and everything in the relation is in A, in script A, which uniformizes f, which uniformizes R. So that really just says that the image of f under this, the image of the infinite subsets of B under this function f is maximal in, this is a typo. So this n here should be B0. This also should be B0 here. Can't. This n here should say B0. Okay. So it says that the image of f is maximal at least on this large set, the tildes of this of the infinite subsets of B0. So we've got a large set in which A is maximal with respect, at least modulo this tilde operator. And actually then by this universal Ramsey regularity, you can assume that f is continuous. That is by a very well-known theorem. Because this function, because every set has a Ramsey property, and then you can just make this function continuous. And you can, of course, also assume that the domain of this function is just Baire space, because you can pick any surjection from Baire space onto this Polish space that the function lived on before. So from now on, we can forget about this complicated domain. We can just assume the function is defined on the Baire space. So that means that A prime is analytic. So A prime is analytic, and it's not a mad family because then we would be done. But it's an AD family, and it's mad in this particular set of these tilde things. And we've got to derive a contradiction from that. So now we want to arrive at a contradiction because we want to show no mad family exists, right? So we arrive at a contradiction by producing a B1 such that B1 tilde has finite intersection with everything in A prime. And this is just, this is really just, here we said A prime is maximal in this set. So now this equation 1 here directly contradicts this. So we want to find this B1, and we find it by thinning out again and again. So here's the second main protagonist of our theorem. It's the invariant tree. So let's write T upper B for the following tree. It consists of the little finite sequences of natural numbers, such that if you look at all the elements in Baire space which go through S, if you apply f to one of these elements, you still hit B tilde. You still catch B tilde. You have infinite intersection still with B tilde. So above S, you still have a chance of producing an infinite intersection with B tilde. So the first observation here is that this tree is invariant. If you replace B by B prime, which is only has finite symmetric difference with B, the tree doesn't change at all. And that's obvious because this defining relation doesn't change, of course, if you change finitely many elements of B. If you change finitely many elements, also finitely and many elements of B tilde will change. Here is claim 2. By Ramsey regularity, you can find B1. This should say subset of square brackets B0 infinity, such that on every further thinning out, the tree doesn't change anymore. So you can make this tree constant. And again, that's by a well-known theorem. It's because by claim 1, the tree is invariant, and we have universal Ramsey regularity. Then you can make the function which assigns the tree to each B constant. This is also very similar to, certain measure theoretic lemmas. All right, and then you show claim 3. Claim 3 is that this tree actually has no infinite branches. And I will say something more about this claim. There is no way of seeing this without saying a lot more. But from this, it follows immediately that we've reached our contradiction. So 1 follows immediately from the fact that the tree has no infinite branches. And that's because, well, if it had an infinite branch, well, if the other way around, if 1 would fail, so if B has infinite intersection with something in A prime, you pick this thing, which supposedly it has infinite intersection with it, that's of the form f of C1. So you fix this C1, f of C1 has large intersection with B1 tilde. Now, the S's, where C1 is contained in the neighborhood, that defines a branch through B1. That's just by the definition. So here you have it. So if TB1 has no infinite branches, then 1 up here has to hold. So this is all that we've left with. We have to show that T has no infinite branches. I call it T star now because it's constant. It doesn't really depend on the B anymore, right? We've made it constant, so I can just call it T star. So we consider 2 cases. The first case is that actually the tree has at least 2 branches. Oh, no, the tree has, the first thing is that that all of the branches of the tree have the same image under F. So the range of F then really just has only 1 set in it. All right, so let's call this set C star. We know now that C star is the unique thing that everything will hit below B1, right? And that's a contradiction. So C star has to be an A because it's the image of F. So by something that I told you earlier, we can find a B2 such that B2 tilde intersect C star is actually empty. Remember, I told you earlier that anything can be thinned out so that its tilde avoids a particular element of the mad family. And here we're using that. So we can avoid this particular C star, but that contradicts actually that the empty set is in the tree. The empty set, the tree has no node. So if we have, if we can find a B2, which is whose tilde is disjoint from C star, the empty set cannot be in the tree, because from the empty set being in the tree, you can just look at the definition. It says here the empty set is in the tree. So it says there is a C in N of empty set that's just vacuous. So there is a C such that f of C intersect B tilde is infinite. Okay, so there is such a C, but all the C's have the same f of C. They're all f of C star by this assumption up here. So we reach a contradiction. So this contradicts that the empty set is in T star, because T star there is only one. There's only one element in f of the branches of T. Okay, and the other case is that there are at least 2 branches. I've handled the case where, no, I should rephrase that. There are branches with different images under F. That's the other case. So I mean, if there are no branches, we're done, right? If all the branches have the same image under F, we're also done. Now, maybe there's more branches with more than one image under F, at least 2 images under F. Okay, so given S, let's write f of S for the longest initial segment common to all f of x, where x is in the neighborhood n of S. Right, so this is the f of S is what you already know about f of x from knowing that x starts with S, right? This is something we do all the time with continuous functions. So because we have 2 branches whose image under F differs, we can find 2 elements of the tree such that the images under F already differs on these two finite nodes. Now I claim we can find two nodes above this pair in the tree. So S0 prime is above S0, S1 prime is above S1 in the tree, such that for any two further above nodes, nothing new gets into the intersection. And this lemma is actually very easy to prove, because if it fails, it means that for any intersection you can extend and get something new into the, for any extension, you can get extend further and get something new in the intersection. So you keep extending and you get more and more in the intersection, and you produce two sets in A with infinite intersection. That's a contradiction. So we know that this lemma is true. So we can find such S1 S prime such that above nothing new comes into the intersection. So in other words, we get this above in the, so by square brackets T, this means the branches in the tree above S0 prime. So you look at all the sets that go into A by applying F to these branches on one side of the tree, and all of them that by the other side, on the other side of the tree, and you take this big union on each side. So this is a subset of N, a very large subset. And this intersection has to be finite, because everything in this intersection arises as such an extension. And there's a common bound on all these intersections over here. Okay, so you've got these two very large sets with finite intersection. And then just by pigeonhole, you can find a thinning out B2 such that its tilde avoids one of these two large sets. I won't go into the proof of that, but that's really easy. That's just pigeonhole, because you can thin out B2 so that either you're inside of this big union, then you're avoiding this guy on the right because the intersection is finite, or you can thin out B2 so that it avoids this set itself. That's just by pigeonhole. Well, then you've avoided this side. So there's always one side which you can avoid. And then again, then you argue very similar as in the previous case, that this contradicts that supposedly Si prime is in T star. Because being in T star means there should be something above which catches B2. And here we said that, you know, we can find this B2 which is not caught. And of course, this uses very heavily that T star is equal to T of B2. And that's because the tree is constant. We've made the tree invariant. All right, that's it. That's the proof. So that's the final contradiction. And we've produced this tilde B2, which witnesses that the mad family isn't maximal. All right, and then we generalized, okay, I'm seeing that am I out of time? No, I'm not. Okay, that's great. I'm doing great with time. So we've also generalized this to what we call higher dimensional mad families. So the finite ideal, the ideal of finite sets, that's just one notion of being small, right? Set theorists talk about ideals. I don't know if you know the set theoretic meaning of ideals. It's a notion of being small. I mean, it means that, you know, an ideal is a collection of sets closed under unions and closed under taking subsets. It's not so important. It's a notion of being small. There are other ideals. For example, this one, fin cross fin. This is called the Fubini product of fin with itself. And we didn't make this up. This ideal plays an important role, for example, in the theory of Borel equivalence relations. There's all kinds of applications of this ideal, and people have asked what happens if you change the definition of mad families, you know, so that you replace the finite ideal by this ideal. And you can do that more generally. You can say let I be any ideal on a countable set S, And then you talk about an I almost disjoint family. It's of course a collection of sets which are large with respect to I. So, but the intersection of any two elements of script A is small with respect to I. So they're I almost disjoint. And then of course an I mad family is a family which is maximal among the I almost disjoint families and infinite. And then you can ask, for example, what about Finn square mad families? And Michael Hosak, for example, asked this. Of course, you can talk about Finn cross Finn cross Finn if you like. And the good news is that the proof that I just showed you can be adapted to work for all of these ideals. So in fact, let F be the smallest collection ideals closed under taking these Fubini products and containing the ideal of finite sets. Then a similar theorem holds. So supposing ZF and dependent choice, if you have uniformization star for all binary relations in gamma, and you have the Ramsey property for all sets in gamma, then there are no I mad families for any I in this collection F, for any iterated Fubini product of Finn. And the remarkable thing is that we just talk about the ordinary Ramsey property here, right? And the unif star is also, both of these notions are somehow collected to the ideal Finn, but still they control what happens with these IMAD families. Yes, that's it. So here are some of the papers that I've either written or that I'm going to write. So the result, most of what I told you about was in this paper, in the PNAS. But we had an earlier paper where we have some results about determinacy. This one was actually written in 2016. And the stuff about the higher dimensional MAT families is currently submitted to Duke. And we're also working on further papers in this area. So that's it.
Thanks for such a great talk. So any questions?
I have a couple of questions. So the first question is regarding the example at the very beginning about the infinite lottery. So is it true that all math families all have size continuum, or was that just part of
Yes, exactly. Oh, that's brilliant. Yes,
okay.
Exactly. That's exactly true. So if you imagine here that instead of 0, 1 here, you just put the natural numbers. So you put a list of entries.
Right.
Then there's no ever winning lottery ticket. Then by a very simple procedure, you can produce a draw, which will be almost disjoint from anything in this list.
Mm-hmm.
So
right.
finite, there are finite MAD families. They're very trivial, like the even and the odds are these two sets constitute a MAD family of size 2. Well, it's not a MAD family because it's not infinite, but it's a finite MAD family. There are no countable MAD families. That's a very old result.
Right, but I guess I mean, but what I asked was a slightly stronger thing, right? Which is that I know that you can't have a countable one, but maybe there's something that's uncountable but not size continuum. Or... Oh
yes, you can have that too. Yes, that's absolutely. Yeah, I mean,
okay.
You can force and you can have anything you want.
Right. That's what I thought.
Right. You can have the continuum be Aleph 2, and so the size of the smallest MAD family is called fractor A usually. Mm-hmm. That's what's called a cardinal invariant, and you can have A is less the continuum, of course. So
right. Okay, and I had a second question regarding this unif star. So, I mean, it's an extra assumption that you have to make, right? Do you have
this unif star? Yes.
Yeah. Do you have any simple upper bounds on what things imply unif star?
Yeah, that's a really good question. I mean, I said it, I wrote it here, I forgot to say it. It's really not very strong. It holds in Solovey's model. Mm-hmm. So, okay. You don't need large cardinals for this.
Right.
This is because of the star. If you take away the star, uniformization in the context of regularity properties is very strong, you know, but if you just have the star, it doesn't seem to be so strong. But there's a lot, you know, this is kind of, I don't think this has been considered very much, this UNIF star. So one could probably ask a lot of interesting questions about it. I don't know how to force it, for example, without, you know, going to Solovey's model.
Right. Cool, thanks.
Any more questions?
Can I ask one? Oh, sorry.
Yeah, you go ahead.
Does there have some relation to the maximum independent family with the Ramsey regularity?
Oh, I have no idea. That's a very nice question. That's a good research question. I will think about it. Yeah, thank you. I mean, maybe this is known, and I assume that the answer is no, because maximal independent families, my intuition is that it has more to do with Baire category than with Ramsey-ness. But yeah, I don't know. I'd have to think about it. Off the top of my head, I don't know.
Okay, Xianghui. Yeah. You can ask a question.
So my question is your uniform star. So you said it holds in follows. Does it follow from 80, or I guess it follows from 80 plus, right?
Oh, that's another good question. No, I don't think it follows from. So that is also a very good question.
So
I said,
Itai and someone else result that the in LFR. Yeah, that one.
yeah. So here, so it's this side of the whole business that
they did it in a
uniformization
different
comes
way,
from.
Oh, by the way, this is wrong. The statement is wrong. You just highlight.
Oh,
The
really?
parenthesis will be 80.
Yo, I
implies-
forgot V equals, yeah, I mean, 80 in L of R implies 80 plus in L of R. This is what I meant.
Yeah.
What is that your complaint?
No. What I'm saying. Okay. I guess it's fine. This version is fine. I'm just saying that 80 implies 80 of R holds inside L of R. So yeah, this version is fine.
Yeah, I know it's fine. Yes, yeah, but
yeah.
I got scared for a second. Yeah. Yes.
Yeah. I was just curious. That,
Yeah, it doesn't imply 80. I mean, so if 80 holds in L of R, it certainly doesn't imply 80 plus holds anywhere except in L of R, anywhere outside. Yeah, if that's what you were thinking that I wrote. I didn't write that, luckily.
Yeah, I was regarding the first question. I was just curious that the way that Itai, I mean, Neiman and No show that they actually show that in L of R plus the AD, right? That there are no math families. I was just curious that your uniform star has anything to do with the 80 plus or some 80 like assumptions.
Yeah, unif star has something to do with 80 plus. Yeah, I mean, I have to say, I would say that
I mean, 80 and 80 plus.
So this is actually something that is kind of hairy. I mean, that's a kind of weird thing. So, I mean, I'm not entirely sure. So I'm sure that 80 plus implies enough of unif star that you can rule out the existence of mad families. I don't know if it implies unif star outright. It might. I haven't thought about it.
Okay.
No, if it does, it would do so by sigma 2-1 reflection. If there's a counterexample to unif star, you know,
it's gotta be very,
you use sigma 2-1 reflection, maybe there should be a delta 2-1 such counterexample, and that's not possible. So probably 80 plus does imply unif star.
Another one. Do you know anything about the your talk is about no math family. Anything about Ramsey properties? Because it's open that 80 doesn't imply. Oh, not known yet. 80 implies Ramsey's property.
Oh yeah, I wish I knew something.
I mean, do you know anything like in the Solovey's model? Is it true? Maybe
The Ramsey property. Oopsie. The Ramsey property certainly holds in Solovey's model. Yes. That was one of the things Matthias showed.
Oh, right, obvious.
And 80 plus implies every set has the Ramsey property. 80R implies it. I mean, but yeah, if 80 implies every set has the Ramsey property, that's a very old and very open question.
Right. Yeah, you're right. This math test showed that. Yeah, that's all my questions. Thanks.
Thank you.
Okay, thanks. So thanks for your talk. And the next speaker. Thanks, David.